This is the first video in a series devoted to topology, more specifically point set topology, at least for the start that is, taught at the advanced undergraduate level. And today we're going to look at the notion of an open set. But before we do that, I'd like to look at a theme that will be running through everything that we do in this point set topology section. And that is, many ideas in point set topology can be seen as axiomatizations of natural characteristics of the real numbers. And we'll see that today with the notion of an open set in a topological space. And the path that we'll take is to look at open intervals in the real numbers. That's something that everyone's familiar with from even a high school algebra class. We'll use that to define the notion of an open set of real numbers, and then we'll axiomatize that into the definition of open sets in an arbitrary topological space. Okay, so let's start with open intervals in real numbers. So let's take two real numbers, A and B, and we'll define the following types of open intervals. The first will be denoted by parentheses A and B, and that's defined to be all real numbers x where x is bigger than A but less than B, and it's strictly bigger than A and strictly less than B. And the standard way of graphing this, if you will, would be to build a number line where A and B are on that number line, and then put open circles around both A and B, meaning we are not including A and we're not including B, and then shade everything in between. So that means we're including everything between A and B, but not A or B. Okay, and then after that, there are four, or I should say, three different types of infinitely long open intervals. There's one that starts at A and never ends, so we would write that as A comma infinity. And that's just going to be all real numbers x, where x is bigger than A. And we can draw that pretty easily just by putting A on the number line, an open circle around A, and then shading everything to the right of A. So maybe we would do that as follows. And then we could have infinitely long in the other direction. So that would be minus infinity ending at B. And so we could write that as all real numbers x where x is less than B. And it's got a pretty similar graph. It just ends at B instead of starts at B. So we've got an open circle there. And then we've got this maybe ray pointing over to the left. And then of course, we've got the whole real line, which would be the set minus infinity to infinity. And I don't really think that I need to graph that. And now I'd like to look at the following maybe intuitive observation. And that is, for any point x in an open interval and any type of open interval that we see up here, we can find another interval centered at x completely contained in the original interval. And so, well, what does that look like? Well, for instance, let's go up here and say that we've got a point x somewhere between A and B. Well, since it has a positive distance from both A and B, we could perhaps find the minimum of those distances, take some maybe portion of the minimum of those distances, and create an open interval centered at x that most definitely doesn't land on any of those points outside of that interval. So it would look something like that. And then, well, we could do something similar for all of the rest of these as well. So that would look something like that. That's definitely all within that open interval that we have here, and that interval is centered at x. The new interval is centered at x, we should say. And then we could do that for this other infinite interval or all real numbers kind of clearly. Okay, so our first goal is to take this intuitive observation and write it into something that's a little more mathematically careful and see if we can prove some results regarding this more mathematically careful way of writing this down. Okay, so here's a careful way of writing that intuitive observation down. for any point x on the open interval from a to b, there is a number delta which is bigger than 0, so that x minus delta to x plus delta, the open interval defined as that, is totally contained in our original open interval from a to b. And I'd like to point out that this is most definitely an open interval centered at x. It has radius delta, if you will. Okay, so I've drawn 2 copies of our original interval from a to b just to get some sort of intuitive feel for how we're going to write this proof down, because it really breaks into 2 cases. The first case is exhibited by this picture where x is closer to a than it is to b. And the second picture, well, is if x is closer to b than it is to a. And in this first case, what we'll do is take our delta to be the distance from x to a. So we would maybe say that length right there is delta. But then since our interval has to be centered at x, that means we're going to extend this off the same distance, delta, in the other direction. But since x is closer to a than it is b, well, then this is not going to overlap the b point. And then, well, we're going to do something essentially the same, just maybe the dual of that over here, where we'll say this distance right here from x to b is delta, and then we've got to extend that off the other direction as well. And so let's see, for this magenta one, the magenta interval would be our interval x minus delta to x plus delta. And then this other picture, this is our blue interval x minus delta to x plus delta. And this first one is playing the role of x being closer to a than b. And then the other one, the blue one, is playing the role of x being closer to b than a. That being said, we can smush those together with the minimum function. So let's see how that goes. So let's say we're given some arbitrary point x from our interval from a to b. Then what we want to do is set delta equal to the minimum of the distance from x to a and the distance from x to b. So the distance from x to a is simply x minus a, because x is on the right. And the distance from x to b is b minus x, because, well, x is on the left in that case. And now what we want to do is show that the interval centered at x with radius delta is totally contained in our original interval. Okay, so how can we do that? Well, we can do that with the general proof of set inclusion. So let's take some arbitrary y on the interval from x minus delta to x plus delta. And, well, to finish everything off, what we'll want to show is that y is most definitely between a and b. So this is a little bit overkill, but I think it's good to do proofs a little bit overkill at the beginning while we're getting used to it. Okay, so now let's observe the following first, based off the fact that x is the minimum of those two. Or sorry, delta is the minimum of those two. So let's observe that since delta is the minimum of those two, it's going to be less than or equal to both of them. That's just very quickly from the definition of the minimum. So that means x is less than or equal to, or sorry, delta is less than or equal to x minus a, and delta is less than or equal to b minus x. Okay, well, if delta is less than or equal to x minus a, that means minus delta is bigger than or equal to a minus x, just by negating. And this inequality is what we're going to need to really write everything down. Okay, so now let's notice the following calculation finishes it all off. So let's observe that a, well, a is going to be equal to x plus a minus x. Okay, so I think that's pretty clear. We just added 0. But now we can replace this a minus x with this minus delta, and that pushes everything bigger. So this whole thing is going to be less than or equal to x minus delta. But now since y is on the interval from x minus delta to x plus delta, that means y is bigger than x minus delta. Then it's also less than x plus delta, again, because it's on that interval. But now what we can do is replace delta with b minus x. So this is going to be less than or equal to x plus b minus x, which is equal to b. So we've got this big inequality right here, and now let's look at some fairly important parts of it. We've got a is less than y, which in turn is less than b. So maybe cutting out the middle, if you will, you'll see that a is less than y, which is less than b, which is the condition we need for y to be inside of the interval from a to b. So if we started with an arbitrary element in this interval, we ended with an arbitrary element, or that arbitrary element is in our larger interval, then what that means is that x minus delta to x plus delta is in fact a subset of the interval from a to b. And we finished all that off. Okay, so now what I'd like to do is take this claim that we proved about finite open intervals and use it to define the notion of an open set in the real numbers. So what we've done so far is shown that open intervals, or finite open intervals, satisfy this really nice condition within the real numbers. And now we're going to axiomatize that condition to something that we'll call an open set in the real numbers. So here's the definition. So we say a subset of real numbers u is open if for all x in u there is a delta bigger than 0 such that the open interval x minus delta to x plus delta is contained within u as a subset. And so let's observe that we just proved that the open interval AB is an open set. And that means we haven't really misused the word open, really. The word open in set here comes from the idea that this open interval kind of already existed. Okay, so now I'd like to look at some other types of open sets. And well, we're going to look at 5. So the real numbers is an open set. The empty set is an open set. These infinitely long intervals are open sets. And then, well, that union of a bunch of open intervals is also an open set. So let's prove each of these. Okay, so starting with the real numbers. So let's say we are given a real number x. Let's note that the interval from x minus 1 to x plus 1, well, that's most definitely contained within the real numbers. So in other words, we could just use delta equal to 1 here, and that's because this thing is infinitely long. There's nothing really fancy to do. Okay, so now let's move on to the empty set. Now let's carefully look at our definition over here. It says, for all x in u, there is a delta bigger than 0 such that some stuff happens. But to show that this is open, we need to show for all x in the empty set, some stuff happens. But observe that there are no x values in the empty set. But what that means is our condition over here is so-called vacuously true, because we can't set up the conditional, so we consider it to be a true statement. So really there's nothing to do here, and like I said, this is just vacuously true. Or I guess I should say the condition over here is vacuously true, and thus the empty set is an open set. Now let's move on to the set A to infinity. And this isn't too bad. Let's take a value x in the set A to infinity. And now let's look at the picture here. So let's say here is A, and then the open interval from A to infinity has the following picture. And so x is going to be somewhere bigger than A, so it's perhaps there. So we might as well take delta to be the distance from x to A, and then we can extend that off in the other direction as well. And that'll definitely be contained in both directions. One direction, because, well, we measured it just exactly to the end point, and to the right because, well, this interval never ends. So we can do that in the following way. So let's set delta equal to x minus a, and let's note that we pretty clearly have x minus delta to x plus delta is contained in our interval a to infinity. Now, you could check this more carefully like we did for our original open interval argument, but I'll leave that to you. And then, well, what about this? Minus infinity to b. Well, I'll just say that that's similar and put a check mark next to it. Now, what about our last thing, our union of a bunch of open sets? Well, I'm not going to prove this. Maybe I'll talk our way through it. So let's say that x is in this union. Well, that means that x is in one of those intervals. But if it's in one of those intervals, we can just apply our claim from before to produce that delta and everything will work out. I'm not going to do this because we're going to do this, in fact, more generally later. Okay, so now what I want to do is negate this definition of open to get an idea for some sets that are not open. So in order to get an idea of what sets are not open in R, let's carefully negate the definition using strategies that you might have learned in an introduction to proofwriting class about how to negate logical statements. So we say that A, which is a subset of real numbers, is not open if there is an x in A such that for all delta bigger than 0, that interval x minus delta to x plus delta is not a subset of A. So let's compare that to the definition of open. So observe, we took this for all statement for all x in U and we changed it to an existential statement. There exists an x in A. That's what you do when negating. For alls turn into there exists and vice versa. So that means we changed this there exists a delta bigger than 0 and changed it to a for all delta bigger than 0. And then we took this containment here and we turned it into a not containment, if you will. Okay, so now that we've got a definition for not open, let's show some sets are not open. And let's observe over here, by the definition of not open, it just says there is an x in A where some bad stuff happens. So that means, well, we could potentially just pick out a carefully chosen value of each of these sets where the openness does not work. Okay, so let's start with the integers. And let's say, well, we could focus on the point 0 in the integers. So I'll just say that we're going to work from the point 0, which, like I said, is most definitely an integer. And let's make sure to take any delta bigger than 0, because this kind of thing has to occur for any delta bigger than 0. Okay, then next up what we're going to do is find a natural number n satisfying the following condition, and that is delta over n is less than 1. Well, notice that if delta is bigger than 0, we can always scale it down by dividing it by a natural number until we are less than 1. And then we're left with the following calculation. So let's observe that 0 is most definitely less than delta over 2 times n. I think that's pretty clear because delta is bigger than 0. But in turn, that's less than delta over n because it's dividing by a 2. But that's going to be less than delta. But then what does that tell us? That tells us that delta over 2 times n is on the interval. Well, it's on the interval from 0 to delta, but specifically it's on the interval from minus delta to delta. Okay, but then also, what do we know? We know 0 is less than delta over 2 times n, which is less than delta over n, which is less than 1. And that's because of this condition right here. So that means that delta over 2 times n is on the interval, let's see, from 0 to 1. But notice that if it's on the interval from 0 to 1, not including 0 and not including 1, what that tells us is that delta over 2 times n cannot be an integer because there are no integers between 0 and 1. But let's see, we've got our delta over 2 times n is in our interval and it's not an integer. But what that means is that our interval cannot be a subset of the integers. But there we've done it. We've done the condition that z is not an open set. Okay, now let's move on to one of these closed or half-closed intervals. Okay, so now let's look at this closed interval from A to B. And actually, while I use the word closed, I'd like to point out here that this definition of not open, I did not use the word closed. That's because not open and closed will not be the same thing in this topological setup. Okay, so we're showing things are not open at the moment. Okay, so here we're gonna work from our point A, which is in the closed interval from A to B. It makes sense that we would work from A or we would work from B because that's how this interval differs from the open interval from A to B. It includes the endpoints. Okay, and so now let's take any delta bigger than 0 and let's observe the following that thing that I'll start as a picture, but after it starts as a picture, we'll write it down carefully. Okay, so let's draw our closed interval first. So we got our closed interval from A to B. So instead of having open circles like we did before, we'll have closed circles. That's pretty standard. Okay, so there we've got that. And then, well, since we're working from A, we're going to look at an open interval of radius delta centered at A. So that means maybe we would go over here, and then this distance right here would be delta. So that means this point right here would be A plus delta, and then we've got to go back in this direction as well. And then this point right here is going to be A minus delta because this is also length delta. Okay, nice. And now, well, what do we see? Well, there are a bunch of points, like for instance, all the points right here are not in our original closed interval. But if they're outside of our original closed interval, then that means that open interval A minus delta to A plus delta cannot be a subset. But let's write that down carefully. So let's note the following. A minus delta over 2 is most definitely on the interval from A minus delta to A plus delta. I think that's pretty clear that A minus delta over 2 is on that open interval. It's perhaps the one that we've just drawn right there in yellow. But what do we also know? We know that A minus delta over 2 is strictly less than A, but if it's strictly less than A, then it cannot be on the closed interval from A to B. But that means that our A minus delta to A plus delta cannot be a subset of our closed interval from A to B. But that's exactly what we needed to do to show that it satisfied this not open definition. So maybe notice that we worked everything off of the picture here. And that's kind of a theme with a lot of these topological arguments, is that you can draw a nice picture first. And after you've got a nice picture, you can work everything more, or maybe write everything carefully down by what you drew in the picture. Okay, so we've taken care of Z, we've taken care of this closed interval from A to B. I would say that this closed A, open B, and this open A, closed B, and those two infinitely long ones are pretty much the same. Let's skip those and finish this observation off with a proof that the rational numbers is not an open set. Okay, so now we're going to show that the rationals are not an open set. And we're going to work off the point 0 in the rationals, because all we have to show is that there exists what I'll call a bad point, and then any delta bigger than 0. And let's observe that when we say any delta bigger than 0, that means that delta could be rational or irrational. So we've got to work those two cases separately. So let's look at this first case when delta is rational. But if delta is rational, then delta over the square root of 2 is irrational. I think that's pretty clear, although I will leave that as a homework exercise. And now let's also note the following, that 0 is less than delta over the square root of 2, which in turn is less than delta. But what that tells us is that delta over the square root of 2 is an element of minus delta to delta. But let's see what we have. We have delta over radical 2 is not rational, but it is on the interval from minus delta to delta. But putting those things together, we see that the interval from minus to delta is not contained within the rational numbers. Okay, so that means that, well, we've shown the not open condition over here if we started with a rational number. Now, starting with an irrational number is actually a little bit easier. So if delta is irrational, then delta over 2 is also irrational. But then we can do the same sort of calculation. We have 0 is less than delta over 2, which is less than delta. But that tells us that delta over 2 is on the interval from minus delta to delta. But then check it out. We've got delta over 2 is on that open interval, but it is irrational. But that means that delta over 2 is, but that means that our interval from minus delta to delta is not a subset of the rationals. But again, that's where we needed to end up. So putting these two things together, we see that the rational numbers are indeed not an open set. Okay, so now what I'd like to do is prove a really classic proposition regarding open sets of real numbers. So the classic proposition we're going to prove now is that arbitrary unions of open sets are open and finite intersections of open sets are open. Okay, so let's prove the union setup first. So what I mean by arbitrary unions is it could be a finite union, an infinite union, and that infinite union could be over any indexing set. Could be natural number indexing set, or maybe real number indexing set, really any arbitrary indexing set. So the way to do that is as follows. So let's say that we are given ui, which is a subset of real numbers, and they are all open for I from some indexing set I. Then what we want to show, so let's maybe get that written down. So we want to show that the union over all I and I of ui is an open set. Okay, so let's see how we might do that, keeping in mind our definition over here of an open set. Okay, so let's say we are given a number x inside of this union. I say number because these are all subsets of real numbers, thus the union is also a subset of real numbers. But if x is in this union, then by the definition of union, that tells us that there exists a j, for instance, in the indexing set such that x is in u sub j. So that means now we've got x is in one of these component open sets, if you will. But we know that u sub j is open, so we can use the fact that u sub j is open to do something like this. So that means there exists a delta bigger than 0 such that the interval x minus delta to x plus delta is contained in u sub j. But now let's observe that if you have a collection of sets and you take their union, then any of the original sets is a subset of that union. That's something that you would prove maybe in an introductory proofwriting class in the sets section. So that means that all of this is a subset of the union over all I and I of ui. But check it out. Starting here and ending over there is exactly what we needed to prove that this union was open. Okay, so we've got that. Now let's prove that a finite intersection is open. And it's really important that we have the word finite here because it is not true with an infinite intersection, and we'll show that later. Okay, so let's say we are given u1, u2, all the way up to un, which are subsets of real numbers, are all open subsets of real numbers. So we've got a finite collection of subsets of real numbers that are all open. Okay, so now let's take an x in their intersection. So u1 intersect u2, all the way up intersect un. But what does it mean for x to be in that intersection? Well, intersection is like an and statement. So that means that x is in u sub k for all k between 1 and n. But now what we'll do is we'll use the fact that u sub k are all open, and we'll get a delta for each of those. So let's note that there exists a delta k bigger than or equal to 0 such that x minus delta k to x plus delta k is a subset of uk for all k between 1 and n. And that's by the openness of uk. And now what we'd like to do is squeeze an interval inside of all of these. And the way to do that is with the minimum. So let's set delta not subscripted equal to the minimum of delta 1, delta 2, all the way up delta n. And observe that since we've got a finite number of things we're taking the minimum of, well, the minimum makes sense and it's bigger than 0. If it were infinite, then the minimum wouldn't make sense. And in fact, we would look for a greatest lower bound, and that might be actually equal to 0. That's why we need the finiteness condition here. And now, well, we can finish this off all really quickly. And that is x minus delta to x plus delta is most definitely contained in x minus delta k to x plus delta k. And that's true for all k based off the fact that this condition right here, this building delta as the minimum, means that delta is less than or equal to delta k for all k. Again, by the definition of the minimum. But then this is contained within uk for all k. But then if that delta minus k to delta plus k is a subset of uk for all k, the important thing is it's a subset of uk for all k, then bringing the last step up here, we have x minus delta to x plus delta is a subset of the intersection of all of these uk's as k goes from 1 to n. Okay, so that's the last thing that we needed to show that a finite intersection of open was open. Now, let's maybe look at why we really need the word finite in that finite intersection condition. So here's an example why an infinite intersection of open sets may not be open. And we'll do that by showing the intersection as n goes from 1 to infinity of the open interval from minus 1 over n to 1 plus 1 over n is in fact the closed interval from 0 to 1, which we showed is not open. So notice we're intersecting infinitely many open sets and producing something that is not open. Now let's observe that it's pretty clear that this right-hand set is a subset of this left-hand set. Well, it's a subset of all of them. There's not really much to do there. So that means to show this equality, we need to show that this intersection is a subset of the interval from 0 to 1. And we're going to do this by using the contrapositive. And so, meaning the contrapositive, what we'll do is show that if x is not in the set from 0 to 1, then x is not in this intersection in going from 1 to infinity of minus 1 over n to 1 plus 1 over n. So that would be the contrapositive of the usual straightforward way of showing set containment, but it's a little bit more natural to do it this way. Okay, so let's start with that contrapositive proof. So let's suppose that x is not in the set from 0 to 1, but that means that x is either strictly less than 0 or, let's see, x is strictly bigger than 1. So let's break these into cases. Maybe I'll do one case and I'll leave the other one as a homework. So let's do the case when x is less than 0. So if x is less than 0, then that means that minus 1 over x is bigger than 0. So we've got a positive real number. But if we've got a positive real number, then that means that we can find a natural number, capital N, that is larger than that real number. And that's by something called the Archimedean principle. There's always a natural number bigger than every real number. So we've got n is bigger than minus 1 over n. But then moving some things around, we see that minus 1 over n is in fact bigger than x. Again, that's just by reciprocating and negating. But if minus 1 over n is bigger than x, then that means that x cannot be on the set from minus 1 over n to 1 plus 1 over n. That's because it's smaller than the left-hand endpoint. But then if it's smaller than the left-hand endpoint, it is not on that open interval. But look, we found one of these open sets that does not contain x. But that means that x is not in the intersection from 1 to infinity of these open sets because it's not in, well, the one that we just constructed. Okay, and then, well, like I said, there is a case 2 as well, but perhaps I'll leave the case 2 as a homework exercise. And that would be the case when x is bigger than 1. You do the same kind of thing. You construct an interval that ends before our value of x. Okay, so now what I'd like to do is take this important proposition that we just had and axiomatize that into the notion of an open set, or more generally a topological space. So let's see what we've got. We proved this, what I called an important proposition regarding open sets of real numbers. So the empty set and then the real numbers, they were both open sets. An arbitrary union of open sets was open, which can technically be written as follows. And a finite intersection of open sets was also open. We just finished proving both of those. Now I'd like to axiomatize that to a definition of an arbitrary topological space. So a topological space is a set X, and that could be a set of anything, together with a collection of subsets which we'll call T. So everything in T is a subset of X. And the elements of T are called open sets, or the open sets of X maybe. And those open sets, or this collection T, satisfies conditions built out of these conditions up here. So first, the empty set and all of X is an element of T. In other words, those are both open. If you've got ui, an element of T, for all I in an indexing set I, then the union of all the ui's are also an element of T. So in other words, arbitrary union of open is open. And then if you've got a finite number of sets in T, u1 to un, then their intersection is also in T. In other words, finite intersection of open is open. Okay, so in upcoming videos, we'll look at other topological spaces other than the normal one of real numbers, obviously to give us some more examples. But this is like the final part of the material that we'll see today, but I will leave you with some exercises. So I've got 6. The first is to show that the interval from -infinity to b, not including b, is open. But if you include b, it's not open. Next is to show that any singleton is not open. So that would be the singleton containing x. And then here's a part of a proof that we didn't prove that I'd said I'd leave for a homework exercise. And that is, if you have a rational number delta, then delta over the square root of 2 is irrational. And then let's prove another example of infinite intersection of open, not open, by proving that the intersection from 1 to infinity of -1 over n to 1 over n is just the singleton 0. And then here's a companion to that involving closed intervals. The union, as n goes from 1 to infinity, of the closed interval from 1 over n to 1 is half open. It does not include 0, but it does include 1, kind of obviously because it goes up to 1 there. And that's a good place to stop.